Our next speaker is Aayush Kumar Jaiswal. I don't know, maybe you can explain if this was spelled correctly. And he currently works at the research scientist at VTT Technical Research Center of Finland in the biomaterial processing and product research area. His works focus on application development for cellulose nanomaterials in packaging, electronics, optics. And he's also involved in upscaling these developments, also obviously to a different market like we have here, the glass industry. And he comes from the IIT Roorkee in 2017. He graduated there, and he's from the pulp and paper technology. And his talk now will about adaptive passive cooling, cellulose-based films for smart windows, so an application with paper in combination, or cellulose in combination with glass. So we're looking forward to this one.
All right, I take this up with me. Yes, good afternoon, everyone. Pleasure to be here. And so firstly, I'm not involved with glass industry at all. So this is really a pleasure to be here and experience what the glass industry is about. But before we go into the details a little bit, I want to talk that you might be wondering that what is this thing, VTT. So it's the Technical Research Center of Finland. So it's we are owned by the Finnish state, by the Ministry of Economic Affairs and Employment, when you translate it. So rather big institute. We have about more than 2,000 employees, maybe 1,500 of scientists, staff, and we are working in about 50 plus research areas. And one of them, of course, is something that I'm going to talk about, and which is what I'm doing. We are located here also in Tampere and many other Finnish cities. So it's pretty clear that these cooling needs are growing exponentially, and the best answer to cooling our living spaces that we have here is active cooling, so air conditioning. But if you think about the scale at which air conditioning is scaling up, so the IEA, the International Energy Association, predicts that we're going to have so many air conditioners in the world by 2050. So it's equivalent to selling 10 units per second for the next 30 years. So that's the amount that we're talking about. So something has to be done about the energy consumption related to cooling. And of course, one thing is that you can always use renewable energy to cool, but is there enough of that? So we have to help these active cooling systems with some passive cooling systems, and this is not new. There has been huge amount of work done already with passive cooling. But then comes a specific part of this passive cooling, which is passive radiative cooling, and especially how to do it in the daytime, because radiative cooling is happening all the time. This is how our planet cools itself during the nighttime. And then this big breakthrough in this field came less than a decade ago from Stanford, where these kind of structures could be made, which are actually very good emitters in this 8 to 13 micron wavelength range, which is the transmission window of the Earth's atmosphere. So what it essentially means is that a system like this, where you have the solar gain, of course, you raise the temperature by absorption, and then if you have the emittance in this certain 8 to 13 micron range, you can actually use the coldness of the space as a heat sink. So you can basically throw your heat out back to where it came from the sky. And this was a major breakthrough in this daytime radiative cooling. But then comes this aspect of what we are bringing here to the table. It's this cellulose-based adaptive passive cooling. And the benefits here is that it's, of course, functional. It serves a function. It's completely derived from plants. So it's a plant-based raw material, fully renewable. And at the same time, you can recycle. So I can show that how it improves the recyclability of the coated glass. So firstly, so in this audience, I would want to show what this cellulose is. So basically, it's the main strengthening component of a plant. So you can find it in woods, woody plants, trees. You can find it cotton, hemp, all kind of non-wood plants. So it's the fibers which are basically giving the structure to all the plants. And cellulose, in this sense, is the most abundant biopolymer on Earth, and it is being continuously regenerated with vegetal growth. And you might know cellulose very commonly with something like this, so your office paper. But the key thing is that how do we get something like this turning into like this, an optical film, so fully transparent. And mind you, these are chemically exactly the same thing. So this is pure cellulose that we are talking about. And how do we do it is by destructuring the plant into so small levels that we start getting to the nanometer range. So we can make both nanofibers or nanocrystals from natural cellulose. And we have been doing this now more than a decade. We can do it in quite large pilot scale. And this is where, when you reach this nano regime, you can start getting materials like this, which can be used with glass. And what these nanomaterials are doing is they're looking something like this on the picture. So they make very strong hydrogels. So, and then when you turn it into films, they are like on the picture there, extremely strong, very flexible. So you can basically do whatever you want with this. They are transparent. Haziness can be tuned with the formulation. It's a completely water-based process that we are talking about. And there is no binder needed, so these materials are self-assembling. You just throw them onto the glass, dry it, and then they turn it into a film. They self-assemble. And now comes this interesting feature. Why are we applying it to radiative cooling? Is that cellulose as a material, which we have figured out, also has this 8 to 13 micron range where it's emitting, and which is also corresponding to the atmospheric transmission. So there is proven potential for radiative cooling, and which has already been shown actually by other research groups. And this is basically our case that, okay, we have a film, we can coat this also on glass, we can laminate it as well, and we can get some cooling, but can we add some more functionality to it? So as a case, we jumped into thermochromics, quite well known for these smart window applications. And then when we combine these two class of materials, we get this so-called thermoresponsive cooling films. On the bottom is actually it's not accelerated, it's a real-time video, just heating the film with a hair dryer, basically. So we can have a tunable response temperature. So here we are not talking about 60, 70 degrees of transition temperature. Here we are talking about 20, 30 degrees, but it's tunable. We can go from as low as 15, as high as 80 degrees in the transition temperature. And of course, then the reflectivity of the film can also be increased by adding some coating. So you can actually metallize the film as well. And then we started studying the cooling potential for this. So we made a very small lab setup. We are in Finland, so there is not so much of sun, so we have to use a solar simulator running these in winter. So just having kind of a window cut into insulated box, and then just loading it with a lot of thermocouples and measuring how the temperature evolves inside. And we just put the samples basically on the window on the top. And this is one example of what we can do here. So if you look at the graph on the right, on the top is the plain, so float glass. And then this commercial samples that we are using, comparing it's this low-E coated glass. And if you look at this our samples, which is this CNF TC, so we are almost in the same ballpark of cooling as we can get with a commercial solar film with 5% transparency, so about 4 to 5 degrees of cooling effect in this test. And when we start metallizing the film, we are getting absolutely no temperature gain. But of course, when we are patterning it, so you're always losing a little bit transparency when you're increasing the cooling potential. But even with very clear films, we can go something about 4 degrees cooling. So in this experiment, we are simulating, for example, you can think that your car is parked for 10 minutes in a bright sun in the summertime. So you can save quite some energy in cooling there. And then when we talk about the adaptivity, then we have basically the same setup. We can also do this outside when we want cold temperatures. So there is clear difference between the sample front side and the back side when we are talking about the cooling effect. And also we can see that the temperature dependent reflectivity, how it evolves. So we use a very simple setup here. We just use a laser and then we induce heating to the film, so optical heating. And as we start increasing the power of the laser, so just heating more and more, we start to see how the back reflection is increasing. So we can modulate it for now up to roughly 10% change in reflectivity with temperature. So there is, of course, clear thermochromic effect that we expect. And then we decided that we can just put this out to the sun. So we made this kind of inverted aquariums and covered them with our film with temperature loggers, put them in the sun for during the daytime and the nighttime. And these measurements were done of course, in the Finnish climate in south of Finland. And we can see basically the cooling effect done by this blue curve, for example, there. And at nighttime, something interesting happens. We are actually going below ambient because that's a quality of this cellulose as a material itself that it's basically doing radiative cooling. Of course, glass is doing that as well. So, and then we collected all of this data and then started modeling with finite element modeling that how can we actually analyze the impact of the solution in different geographies, in different climates. So very simple modeling and trying to look how the heat is evolving inside. So when you have no film blocking the box on the top, this is basically modeling the same box that we were talking about earlier. So if the temperature evolves inside the box versus when it evolves just on the surface where you have the cooling film, and then you can extrapolate it. So we have seen that in different climates, of course, it varies greatly the effect, but you can get at least between 1 to 5 degrees of cooling potential in different geographies when you're talking. In Europe, it's about the same, 1 to 5. And then we were starting to think that where can we actually apply this as a combination with glass. Of course, we have standalone films that we can just use. Then we started thinking about this lamination as an application area where we were using PVB as the interlayer, but if we can actually insert our film right between 2 PVBs and then make this kind of laminated structure. At the same time, you can also just coat this material on a glass and then laminate it with using PVB as a interlayer structure. Cellulose, it adheres very well to glass, so there is no issue of delamination there. And then you get something like this, so little bit hazy, but still quite good sample, I would say, for first tests. And then you can also combine this with this, don't have to be float glasses, you can combine it with low E coated glass or tinted glass and so on. And then there is some results related to this laminated sample. So on the top are our reference samples, so the clear float glass samples, there is low E coated and the gray float glass. And then on the bottom are samples those are just to show that you can actually modulate the haziness quite much. So you can have quite clear samples like this one. And then you can also have this kind of film laminate structures where you can make, for example, some privacy windows which are still having some cooling effect. And then we tested these laminated structures in the same setup as we had been testing the films. And you can see that with exactly this sample, you can have quite similar temperature evolution as a low E coated glass, so the reference there. And when you combine them, then you get a little bit more benefit there. And then with this film, of course, the transparency there is quite low, so there is quite much cooling there. But I would say that these coated structures are something that are quite in the same ballpark as we have in these commercial samples. And then also I wanted to summarize all of these into these important points. So first one is that we have shown that you can use actually a renewable material for doing cooling. So this is something that we have not been able to find, for example, in patent literature at all. It's 100% renewable. And now in this conference, I've been hearing a lot about reducing the overall embodied CO2, for example, in the structure. So using cellulose here in terms of LCA, so all this cellulose that you're harvesting from the vegetal biomass, it's all the time regenerating in the nature. So it's in LCA terms having very little impact on the CO2 emission. So it's much better than using a fossil fuel derived raw material. At the same time, we have shown that you can combine this with, let's say, thermochromics. That was just a case example here to get some more functionality like temperature-based reflectivity changes. And you can do both radiative cooling, which we have shown, and you can also do the attenuation-based cooling, of course, here. And the maximum, of course, you can tune how much you want to cool versus how much transparency you have. So, but 1 to 10 degrees we can already measure here. And of course, there is some thermochromic adaptivity there. And one thing is clear that we have quite good adhesion to glass surface, and especially when we have these laminated structures, they are well protected. They are protected, for example, from moisture and from UV if you are using PVB here as well. So, and also cellulose as a material, it's a very good UV absorber, so it's also giving UV blocking properties. And what we have been imagining as the application areas for these are, for example, well, not in the automobile industry, it could be the sunroofs, for example, where this could be applied for having the cooling effect. It could be terraces in the roof side or in the walls. Or this kind of films can also be applied as basically a consumer product that you apply some film directly to your window when it's in the summertime getting very hot, and you can remove those. Or we have also been exploring this concept as, for example, a roll-up curtain and so on that you can use to cool. And finally, I would like to acknowledge the great team that we have behind this. From our silicon photonics and optics experts to all the way to simulations and people who have been developing these nanomaterials for us. And we also have a booth here, so please visit for discussion. We have more samples that you can check out and so on. So thank you.